Welcome everybody. Again, this is ME3331. Today I'm going to be talking about a new subject, which is the second law of thermodynamics, probably the most enigmatic law in all of physics. And so I will do my best to impart this knowledge on you guys, and hopefully you can understand it. I would really recommend reading as well in the textbook to further understand this material. And I will be harping on it probably for the next week or two about first law and entropy, and we'll be continuing to solve problems and to do as much practice as we can in order to really get this concept solid in our minds. Okay? But before I do that, I just wanted to make a couple of announcements. The first is that I am also posting, along with this lecture today, our second experiment that we were going to do in class, but then because of coronavirus and because we are essentially shut down on campus, I had to do in my basement. You hopefully will find that to be interesting and entertaining that video. And I just recorded it, so I'll be posting that up with the data. And the analysis of the data for experiment 2 will be your homework assignment for Monday, okay? So there will be no homework assignment that goes along with the lecture per se. It'll be all based on this experiment that we did, which is material that we've covered a couple weeks ago. So you should be able to do the experimental analysis, no problem. And, excuse me, it should be really an easy thing for you to take care of, okay? So that's the first thing. Discussion you had today, hopefully that went well. I know that Masa was giving the discussion today, and hopefully that goes okay. And the third thing I need to talk about is a little bit about the survey, which I guess I always review here at the beginning of lecture. So today, let's see, let's go here. So I have my YouTube channel. I'm downloading my experiment right now. We'll go here to chime in. Okay, so this was the survey from yesterday. Well, that'd be Wednesday. Which of the following only one is not true about filling an initially empty balloon with helium from a high pressure source over some time t? Okay, which is not true about this? And so we did this analysis as part of the class. I did a little sketch of my kids getting balloons, and we did this analysis for the transient problems for the first law. Right. Okay, so the choices were the mass of helium that enters over time t is equal to the mass of helium in the balloon. Well, yeah, so that is true, because if you have mass going in over some period of time, we assume that that is the mass of helium in the balloon at time t2. I guess we have to assume an initially, oh yeah, I do say initially empty, haha, so I do say initially empty, you see? So that means that essentially that first one is true. The second one, the work term in the energy equation is 0. I specifically said this in the lecture, so if you didn't watch my video, you probably didn't get this, but since the balloon is expanding, there's PDV work, meaning that there's work that's being done by the air going into it, or the helium in this case, by the balloon, okay? So that was the correct answer. Most of you got it right. The third one, the enthalpy times the mass exiting the balloon is 0. Yes, this is also true. Because the enthalpy times the mass exiting the balloon is 0, because there is no leak in the balloon. Got it. Okay. The heat term in the energy equation is 0 if the balloon filling process is assumed to be adiabatic. Nobody should have gotten this one. If you selected this one, you've got to check and make sure whether you know what the term adiabatic means, okay? Let's get with the picture, guys, but most of you got this right. I think 41 correct responses, that's a pretty good rate, especially for the online classes. When we were in the classroom, as I said, this was 100%, but okay. All right, so let's move on. So transient analysis, make sure you practice. You did something for discussion today, make sure you continue to do practice. This is not the last time you're gonna see a transient problem, so just to let you know. All right, chapter 5. So in chapter 5, we're talking about the second law of thermodynamics. As I said, kind of an enigmatic law, kind of a law that many people say they don't understand. I'm going to try to explain it as simply as I can using the slides here plus some whatever I can to help you understand it. We're going to do one example problem today. Since I already did another video lecture, I'm running out of time today, so probably this lecture may not take the full 50 minutes, but we'll see. It'll take what it takes. Okay, so it's the benefit of having these pre-recorded lectures. I can make them any length I want, so long as you'll watch them. Okay, so let's get going. So in chapter 5, what are we going to learn? Chapter 5, we're going to have the key outcomes be to explain the key concepts related to the second law of thermodynamics, including the alternative statements of the second law, because there is no one statement of the second law, as you'll find. So that's what also makes it a little enigmatic. The internally reversible process and the Kelvin temperature scale. Okay, we're going to list several important irreversibilities. Those are things that cause a system or a thermodynamic process to be not reversible, and we're going to learn what reversible and not reversible means. And we're going to evaluate the performance of power cycles and refrigeration heat pump cycles using key corollaries. Now, we're not going to do cycle analysis per se, but what we're going to do is that we're going to look at the temperatures and that the cycles are exchanging heat with, so temperature sinks, and derive certain things about these cycles based on that. And you'll see what we mean by that. We're going to describe the Carnot cycle, which is the most efficient theoretical cycle that one can have in thermodynamics. We're going to apply the Clausius inequality. I'm sorry, the Carnot cycle is the most efficient cycle for a power cycle operating between heat sources, okay? And there are other exceptions. Okay, apply the Clausius inequality is the last thing we're going to do. Okay, you may say, this is stuff I have no idea what the heck you're talking about. All right, that makes sense because you've never seen this before. First law, you've seen before. You probably even saw it in high school. Second law, you have not seen before. I guarantee you, unless you've taken some really advanced statistical thermodynamics or chemistry course, you might have seen this. You've probably not seen second law, okay? Entirely new material. So let's do our best here to do a little short primer on this, and then we'll do an example problem, and hopefully you'll get some idea at least of how we get started here. Oops, what happened to me? What happened to me here? I'm moving around. Okay, sorry about that. Okay, here we go. All right. From the conservation of mass and energy principles, mass and energy cannot be destroyed or created. All right, so we know that. These are conservation laws, that the mass can't be created or destroyed. We know that, right? So first law, Q minus W plus H1 minus H2 plus V squared 1 minus V, et cetera, okay? You got that, equals 0. For a process, conservation of mass and energy principles indicate the disposition of mass and energy. But, however, here this is the but, they don't infer whether the process can actually occur. You might say, well, if it meets the laws of energy conservation, then it's all good, right? Well, no, not necessarily, because you can have energy in equals energy out, and we'll explain a couple of scenarios where a cycle will totally be valid according to the first law, but not valid according to the second law, and not actually physically possible, okay? And that's really the basis of the second law, is describing these processes that can't happen, okay? So the second law of thermodynamics provides the guiding principle for whether a process can occur or not. All right, so if there is as I mentioned in the class, maybe in the beginning, we talked about perpetual motion machines. There's a perpetual motion machine of the first kind and of the second kind. The perpetual motion machine of the second kind doesn't violate the first law, but violates the second law, meaning that energy conservation is fine, but it's not a viable cycle based on the second law of thermodynamics, which we'll describe. All right, confused yet? I keep on moving myself around here. All right, put myself back there. Okay, so the second law of thermodynamics has many aspects, which at first may appear a different kind from those of conservation or mass and energy. So one things we can do are predict the direction of processes, establish the conditions for which thermodynamic equilibrium exists. We've talked about equilibrium, you know, like when two blocks are in thermal communication, they are either touching each other and they reach the same temperature. But we can establish the conditions for equilibrium, like phase equilibrium and mixture equilibrium. Determining the best theoretical performance of cycles, so we can actually use the second law to determine how good. So the first law says that you can't get anything for free. The second law says you can't get that good, or you can't even do that well. You have some limitations. There are some maximum efficiencies that you can only achieve. Determine the best theoretical performance of cycles, engines, and other devices. and evaluate quantitatively the factors that preclude attainment of the best theoretical performance. So, like, we can use the second law to decide, well, what's causing the loss? Where are the what we call irreversibilities of the process, like friction, for example. Okay. Other aspects of the second law include defining a temperature scale independent of the property. So we've already been using Kelvin, so a little bit of a spoiler alert, but definitely Kelvin is derived based on some temperature scale that are independent of the properties of a thermometric substance. So developing the means for evaluating properties such as U and H in terms of properties that are more readily attained experimentally. Scientists and engineers, so we're not going to be really doing these things. We're going to be using these things. So these are other aspects that we're probably not going to be doing much about. Okay, scientists and engineers have found additional uses for the second law and deductions from it. It also has been used in philosophy, economics, and other disciplines. That mainly pertains to the idea of chaos and the idea of entropy. So we're not going to get too much into that, but it is a very interesting field of study and something that, if you're interested, we can talk more about if you're interested. Okay. Here we go. So these are the quote-unquote alternative statements of the second law. Okay? So as it says here, there is no simple statement that captures all the aspects of the second law. So there's not, I mean, there is a, we'll get to it. When we get to entropy, we're going to be describing an equation that is like a conservation law. So that we'll introduce it in that way. However, there's no very simple statement of the second law itself, like energy is conserved. I mean, you can say the second law means entropy is conserved, but we don't know what entropy is, right? I mean, we're even hard pressed to find out what energy really is, but there are like some physical ways that we can think about what energy is. Entropy, on the other hand, is really hard to conceptualize, right? So before we get to sort of an entropy conservation equation, we need to kind of decide, where does this entropy thing come from in the first place? Okay, so the three statements that we have are the Clausius statement, the Kelvin-Planck statement, and the entropy statement. Okay, so these are three statements of the second law. Let's start with the first one. Oops. Okay, so you may be hearing my cat in the background. She's here on the floor. She may be meowing at me and scratching my leg while I'm doing this. Okay, go away, cat. Go away. Okay, she wants attention or food or something. I'm not sure. Okay, let's just continue on here. I'll get attacked by my cat. Okay, alternative statements of the second law. Okay, so the focus of chapter 5 is on the Clausius statement and the Kelvin-Planck statement. So in chapter 6 is where we're going to talk about entropy. Okay, so entropy is a statement that entropy is a property that we'll be deriving in chapter 6. Okay, we'll talk a little bit about it, but chapter 5 is mostly just about introducing these different theories and about the Clausius inequality. Okay, like every physical law, the basis of the second law is experimental. So the father of modern thermodynamics, Sadi Carnot, was a Frenchman in the 1800s. He was observing steam engines, whereas also coincidentally where the first law came from, and was observing about them, was trying to come up with ways that we can explain what the maximum efficiency one could attain in a steam engine is, okay? He knew that it wasn't 100% because experimentally that didn't make any sense. We couldn't have a 100% efficient steam engine. So he figured, how do we theoretically figure out what the maximum efficiency will be? Okay, so while three forms are not given directly demonstrable in the laboratory, deductions from them can be verified experimentally, and this infers the validity of the second law. Okay, actually the second law has been derived from fundamental principles statistically for very microscopic processes. So the second law was conceived, but it was not. It wasn't actually proven until about a century later. So until the 1900s did we actually know what the second law, was actually a proven thing. Okay, so let's go to the first statement. Okay, so the first statement, the Clausius statement of the second law, which is what it says here underneath my picture, is that it is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. All right, now this kind of sounds confusing, doesn't it? So this what it means is, okay, you get it that like if you have a hot block and a cold block and you put them together, the heat is going to transfer from the hot block to the cold block, no problem. Now, what if you wanted to go the other way? What if you wanted to say, well, I'm going to transfer heat from the cold block to the hot block, like we do in an air conditioner? Like cool a hotter thing with a colder thing. Oh, that's going to be tricky. So essentially, this Clausius statement says you can't do that. You just can't have natural heat transfer coming from some cold body to a hot body without something else happening, and that something else is work. Okay. So this would be the violation of the Clausius statement of the second law, meaning that you can't transfer heat from a cold body to a hot body without putting anything else in. Okay, so you can't have an air conditioner that runs essentially without a compressor, but without any plug, right? You can't have just a free compressor, a refrigeration system without a compressor. Okay. Now, we need to make a couple definitions before we get into this. The first thing is that we need to define what a thermal reservoir is, okay? A thermal reservoir is a system that always remains at constant temperature. Whoa! Now we get the cat right here. Say hi, kitty. Okay. I think she wants to be involved. Okay. It's pretty funny. Okay. All right. So such a system is approximated by the Earth's atmospheres, lakes, oceans, and a large block, such as a block of solid copper. So essentially what we're talking about is a very large block that we assume stays constant. Okay. The temperature doesn't change of these thermal reservoirs. All right. So we can assume that they remain always at the same temperature, even though we put energy in or take energy out, which technically doesn't exist, right? But it's a concept. Just think about it as a concept, okay? All right, so now on to the Kelvin-Planck, which is the second statement of the second law. So it's impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. All right. Let's think about what this might mean. This is the diagram. You've got some hot thermal reservoir here. Combustion, for example. I don't know. You've got a combustion process. And you're transferring heat into some engine. Okay? And that engine is operating and generating work. Now, that cannot happen without rejecting any heat to the environment. Okay? You cannot just take all of the heat that you put into a thing and just get all of that back out as work. So this would be totally fine. This actually, this and this would be totally fine based on, so this right thing would be totally fine based on the first law. Heat in equals heat out. No problem, right? No big deal. You can't do that, okay? Just like this. Heat in equals work out. What's wrong with that? It's totally feasible, right? You take all the heat and you put in and you get work out. No, you can't do it. Sorry. That's not allowed. All right. So, great. Let's move on. All right. So, the last thing we're going to do today, here we got about 18 minutes. We're going to do an example problem where we kind of get into this a little bit, right? So, how do we demonstrate that one is that these statements are valid or that they are a violation of each other? So we're going to complete the demonstration of the equivalence of the Clausius and Kelvin-Planck statements, meaning that they both are impossible. Okay, they're both impossible, by proving that one proves the other, essentially. By showing the violation of the Kelvin-Planck statement implies a violation of the Clausius statement, and you could do the same vice versa. But we're going to do this way. Okay. Let me get my my pen and my sketchbook out here. Oops. Let's get this thing working here. All right. Now we're just going to find it. Okay. So here's the example, and I will move this over here, and we can do this. All right. So the problem is complete the demonstration of the equivalence of the Clausius and Kelvin-Planck statements of the second law by showing that a violation of the Kelvin-Planck statement implies a violation of the Clausius statement. Okay, here we go. So known. I guess we're going to say we have a system undergoing a cycle. in violation of the, we'll just say KP statement. Okay, so we have a system undergoing a violation of the KP statement, and we're going to show that also implies a violation of the Clausius statement. Okay, so we're going to find that the system as a consequence violates the Clausius statement. Okay, all right, we're going to do this using kind of a theoretical idea. So let's see, engineering model. Let's make a diagram first. Okay, so the way we're going to do this is we're going to have two reservoirs. So you're going to have a hot reservoir, and then you're going to have a cold reservoir. Okay, hot and cold reservoir. All right, now what we have to have is some sort of thermodynamic cycle going on. So we have to have one cycle here. So this is our one that's violating the Calvin-Planck statement. So essentially what it means is that it's a violator, so it's actually going to be taking heat. So we're going to call this QH, and we're going to make some work out of it. Okay? No, this system looks like this. So this is our thermodynamic. So we'll call this CV1, control volume 1. Actually, it's actually a system 1. It's not control volume, right? Because there's no mass passing through it. System 1. Okay, and then what we're going to do is we're going to show that it also violates the Clausius statement as well. So here we go. So we have to have a system that also does the following. So this one violates by taking cold. So the same work is going to go in here. So this work is going to be the work input to this refrigeration cycle. QC and QH prime. We'll call it QH prime, okay? So then we've got now a refrigeration cycle, and this one doesn't actually violate. So I'm going to just make my boundary 2 here. So this is system 2. Okay, so now assumptions. Okay, so our assumptions are one, that we have 2 ideal cycles, right? Let's see, anything else? I guess we're going to say that the reservoirs, cold and hot, are at constant temperature. Okay, we're going to assume they're at constant temperature. Fine. Okay. All right, good. And then what we're going to do is we're going to do some analysis. All right, so here's our 2 systems. So we have system 1 and system 2. System 1 is a Calvin-Planck violator, meaning that it doesn't reject any heat. It violates the Calvin-Planck statement because it only exchanges heat with one source and makes net power. And then we're going to take that power and we're going to put it into a refrigeration cycle. Okay, so the analysis goes like this. So if we take from system 1, so system 1, we're going to take do the first law. So we are going to use the first law. So for this system, essentially, all we've got is heat and work. We don't have anything crossing the boundary. It's steady state. We're going to assume here steady state cycles. Okay. So we assume here that work, did I just call it W? Yeah. So I'm calling work of the cycle is equal to QH for system 1. And system 1 and system 2. So this is totally cool with the first law, right? Q equals W, no big deal. We can totally do that. First law, no problem. So here, the work of the cycle equals QH prime minus QC, meaning like the work that we put in is this negative work minus QH minus QC. So that would be QH would be the heat out minus heat in, which makes okay with our sign convention. So if we combine, hold on, let me just say example 1 continued. Okay, so then we can combine expressions. Okay, and we get the following thing. We get QH prime is equal to QH plus QC. Okay, so this QH prime essentially is QH plus QC. All right, now, next. Now we think, okay, how are we going to say that this implies a violation of second law? Because this system 2 is totally fine. I mean, system 2 takes work and pumps heat from a cold body to a hot body like a refrigerator does. Okay, now what we can do though is if we just take, for example, this hot reservoir, I'll just take this as hot and this is cold, and we make our overall system, so we make our overall system diagram looks like the following. Right, so we have QH here, we have QH prime here, we have and we have QL here, or QC, sorry. So you have QC there, okay? If we do that, then essentially what we've got is, if we just combine those, right, there's work going on, but it's inside the thermodynamic system. So as I said, it doesn't matter what's going on inside the thermodynamic system. If you take the overall system, it doesn't matter what's going on. Okay? So what this means essentially is that you've got a system that looks like the following. So this is cold and hot. You've got a system that looks like this. You've got one engine, or one cycle essentially, that just takes heat from here to here with no work input. We can't have that, right? Can't do this. It's not okay. So that violates the Clausius statement. So you're going to say that the sole result of the combined system, she's back again. The sole result of the combined system is that a net amount of energy, so Q, we'll call it QC, the same heat, right? So QC and QC is transferred from cold to hot. Right? And so this is a violation of, I'm going to say this violates, the Clausius statement. And therefore, the combined system implies that the Clausius inequality, or the Clausius, statement is also violated. Okay, so that's the idea. So we're going to do a few of these kinds of examples. So you don't have any homework due on Monday on this stuff, but use your brain, think about it a little bit. Okay, watch the lecture, think about it. I'm going to have a discussion question for you or two to do on Friday that you can think about to kind of get yourself warmed up for this. We'll do the experimental analysis for Monday's homework, and then for the following Wednesday, for next Wednesday, we will have some problems that relate to these statements and let you try some on your own. But on Monday's lecture, we'll do some more examples, so you should be all set. I will also post the slides as usual and get everything posted on Canvas so that you have all the resources that you need. Okay, well, with that, have a fantastic weekend, and if you have any questions, feel free to write me an email. I'll be on email all weekend, and I'll be happy to answer any of your questions. Okay, bye for now.